Good day, everyone. The theme of my presentation is Search for neutrino counterparts of LIGO Virgo gravitational wave events. 3 observing runs were made by LIGO Virgo collaborations, and the confirmed events were sorted into 2 gravitational wave transient catalogs. The names of the events are shown on this slide. Why do we need to search for high-energy neutrinos from gravitational wave events? The detection of gravitational waves and high-energy neutrinos from the same sources will make it possible to find a connection between the dynamics of gravitation objects and the properties of relativistic flows. The direction of a muon produced in the reaction of interaction of a muon neutrino with matter strongly correlates with the direction of a neutrino. At sufficiently high neutrino energies, the direction to the astrophysical object can be found with an accuracy of 2 degrees. Since the directions to the source of gravitational waves can be reconstructed with an accuracy of tens to hundreds of square degrees, the joint observation of gravitational waves and neutrinos can significantly improve the localization of the source, making subsequent electromagnetic observations easier. Our experimental setup, Baksan Underground Scintillation Telescope, is shown on the left picture. It consists of 4 horizontal and 4 vertical scintillation planes. The planes are covered with standard scintillation counters, and the total number of counters is 3,180. A standard scintillation counter is shown on the right picture. It is filled with a white spirit-based liquid scintillator, and the scintillator is observed by the photo-multiplier tube with a photocathode diameter of 15 centimeters. Muon neutrinos traveling through the rock around the telescope may interact with nucleons to create energetic muons. Since there is no significant background from the zenith angles more than 100 degrees, it is safe to say that muons from the lower hemisphere are the result of neutrino-matter interaction under the telescope. The overall uncertainty of the neutrino direction for the telescope is about 5 degrees. Separation of arrival directions between up and down hemispheres is made by time of flight method. The basic characteristics of the telescope are shown here. The scintillator is based on the Rice spirit. The total mass of scintillator is 330 tons. 3 lower horizontal layers are the interior layers, and their mass is 130 tons, and they consist of 1,200 counters. Counters threshold for inner planes is 8 MeV. For outer planes, it is 10 MeV. The radiation length for scintillator is 47 gram per square centimeter. The effective depth of the telescope is about 850 meters of water equivalent. The energy threshold for muons is about 220 GeV, and the angular resolution of the telescope is 1.6 degrees. How do we search for counterparts? First, we search for neutrino events within 500 seconds from the moment of the gravitational wave event. Then we check if the localization of the gravitational wave event is at least partially in the field of view of the Baksan Underground Scintillation Telescope. Then, if gravitational wave localization and field of view of the telescope do not overlap, we start processing. If they overlap, neutrinos are sought in the region of gravitational wave localization. If there is a neutrino event, a counterpart is found. And if there are no neutrino events, the maximum and minimum upper limits on the integral flux are calculated within the overlap region of the gravitational wave localization and the telescope's field of view. Here we can see different examples of the overlap search when the localization of the source on the sky map is checked against the field of view of the telescope. Colored regions are the 90% probability source localization. Bright regions of the sky map is the field of view of the Black Sun Underground Scintillation Telescope. And on the left two pictures there is no overlap. On the right two pictures there is overlap. The search for points at which the area of the telescope has minimum and maximum values is shown on this slide. The bottom left of the slide shows the overlapping region, in which the blue dot is the point at which the area of the telescope has minimum value, and the red dot is the point where the area has maximum value. We use the area of the telescope to calculate limits on fluxes. We calculate limits using these expressions. On the left picture, we can see the telescope area in different zenith and azimuth angles when muon crosses 3 or more planes. Everything below black line is the region where zenith angle is more than 100 degrees. On the right picture we can see the example of the event when we see muon from the lower hemisphere, and when this muon crosses 4 horizontal planes. The minimum area for the telescope is 72 square meters and the maximum area is 217 square meters. Limits on fluxes have been calculated for muon neutrinos and antineutrinos, and this slide shows limits on fluxes for the first half of the second gravitational wave transient catalog. The second half of limits calculations for the second catalog is shown here. 3 events were out of field of view of the telescope. The first table here contains limits on fluxes for the events from the first gravitational wave transient catalog. 2 events from this catalog were out of field of view of the telescope. The second table contains limits calculations for the 2 events that are first confirmed neutron star black hole mergers. For all of these events, no counterparts were found. And possible detection of neutrinos from sources of gravitational waves will significantly improve the localization of the source, thereby making further electromagnetic observations easier. Until now, no neutrino events from sources of gravitational waves have been detected. Thanks for your attention.